we'll see how it goes. Okay, so this is the L-shaped method. I'm gonna first show it to you, and then break it into pieces, optimality cuts and feasibility cuts. And after you've seen everything, I'll try and explain why it works. I'll be throwing you hints of why it works as we are seeing it, but the proof of convergence is the last piece of the presentation, which we might actually end up seeing on Friday. Okay, so jumping in, we're going to look at the specific case of a two-stage stochastic program. Do you notice anything specific about this formulation? There's one thing, one piece of data that stands out. There is randomness. And it's going to be good for you to start locating where the randomness is, to start thinking about what algorithms you can use to tackle problems. So what is not random in this problem? See, if you think about it, couldn't be random, because if it were, since X is a first stage decision, it would average out anyways. So when I'm making a first stage decision, which is X, you would expect that a well-described problem specifies how much it's going to cost me if I do something in the first stage. But in principle, W could change from scenario to scenario. Also, A and B are not scenario dependent, but again, that makes sense when you're just isolating the first stage and thinking about only what happens in the first stage. You would expect that it's a well-described situation, but when you move to the second stage, the W could very well change from scenario to scenario, but in this presentation, we're going to assume it's fixed. And then the notation is as usual, as we've seen it so far. Okay. So if you write up the constraint set of this problem, it looks like this, and maybe I'll also draw this to make it a bit more explicit. Right, so you have a block A that hits the vector X, and then you have Y for scenario 1, Y for scenario 2, and so on until Y for scenario capital K. The block over here, T1, is basically representing the constraint T1X plus WY equals HK, H1. So I want a block to hit X, I put it here, and this is W for WY for scenario 1, so W shows up here, and so on. So the constraint then T2X plus WY2 equals H2 can be represented here by a block that hits again X, and the W is here, and so on. There's a specific structure about this problem. It has this L-shaped matrix over here. And the rationale of linear programming gurus back in the early days of development of linear programming was that we can take advantage of, this is not just any constraint matrix, it has a specific form. So the idea that they came up with is that we will just solve the problem in a greedy way and ignore what happens down the line. So here, if you think about what kind of problems this structure represents, it's basically a two-stage problem where you first make a first-stage decision, and then that decision feeds into the second-stage through the T matrices. So the idea, the philosophy of the algorithm is, let's just forget about the whole second stage. So just look at this part of the problem. Forget about the rest, and basically what we're effectively doing is ignoring a bunch of constraints. If it turns out that the decision we made by ignoring all these constraints is a lousy one, we add some constraints in this problem that make us help us make a better decision. But the philosophy is just, cut this part of the matrix and drop it. There's a cousin algorithm, and this approach is called Bender's decomposition. Now, if you had multiple stages, again, the matrix would have a specific structure where you could isolate a certain part of the constraint matrix, and we will see a multi-stage version of this. There's a cousin algorithm of this which does something dual to this, which is instead of ignoring a bunch of constraints, it ignores a bunch of columns. So instead of dropping rows, it drops columns. In that case, the structure of the problem is of the constraint matrix is something like this. So it's upper triangular, and that algorithm, which we are not going to touch on in this course, probably is the Danzig decomposition. So these two are cousin algorithms, but when you hear L-shaped method or Bender's decomposition, this is the type of constraint matrix you should be expecting. Okay, so I kind of give you a hint of what we will be doing. We will basically be simplifying ridiculously the first stage problem, making silly decisions, then pushing them down to the second stage, looking to see what happens, and picking up information from the second stage and sending it back in a very structured way. What do we know about the value function of the value function, if you recall, is the function that maps, you tell me your first stage decision X, I tell you what its expected cost is going to be. And strictly the mathematical definition is exactly this. You tell me what your X is, I feed it into the second stage, and I solve only for the Y case. This is the definition of the value function in a two-stage stochastic program. We've kind of seen this in the homework and also in previous lectures, and if you're not aware of it, we will prove it. But at this point of the talk, it's just important to know this and remember it. This v of x has a very specific dependence on x. It's a piecewise linear function of x. So the whole idea of okay, that said, what do you think this problem is doing? You know that the value function is a piecewise linear function of x. Forget about these guys here for a moment, but think about these terms and the objective function. What is going on here? Does this problem look at all like the original problem we have to solve? Come again? There's the C transpose x, there's the AX equals B. We have the non-negativity on x, and now we have this weird theta here. It's doing something specific though. This is a minimization problem. And these constraints have a specific sign. They're greater than or equal constraints. So what can you say about, yes?
Is it a variable?
Come again? It's a variable. It's a variable. If it were a parameter, it would just drop out of the problem. It's a variable. So what when I'm writing out a linear program, like this, geometrically, what am I doing here? Let's draw the two lines, and these are like in our A1 is in R1. So we have, this is A1x plus B1. This could be A2x plus B2. Okay. What am I doing in this linear program? I'm taking the max of the two linear functions. So where is this problem gonna stop? What's the optimal solution to this problem? The intersection. So this formulation here, when I'm using an auxiliary variable and I have a bunch of affine inequalities in the constraint set, what I'm basically describing is a piecewise linear function. It's exactly what's going on here, right? The theta is my auxiliary variable, and I have this theta greater than or equal to affine inequalities. Is that clear? That's important. That's very useful. So now, is this, going back to my original question, given you know v of x is a piecewise linear function of x, and given what I just said to you, does this problem look familiar? It's basically the problem we're trying to solve, right? Yeah.
What is
E? E over here?
Yes.
This is a parameter, as is this here, and it's just basically it's a scalar. It's a single number. So, for example, if my value function I won't even bother with drawing something new. If my value function, if my v of x were this function here, I know before I even attempt to solve the problem, I know it's a piecewise linear function. Fact, believe me, it's true. So in this case, the E there could be the B1, and the capital E would be the A1. Would be the slope. Actually, it would be minus A1. So the question is, if only I knew these numbers. Yeah, go ahead. How do you know that, right? That's what I'm going to show you today. But the thing is, I know it looks like something like this. The question is how we come up with these numbers here. Is that clear, Thomas? So these are parameters, yeah. These are parameters, as are the coefficients here. We don't know them before we start the algorithm, but we're gonna see how we come up with them. Then there's these other guys here, the feasibility cuts, but let's not think about these yet. Okay, we'll see those in the second part of the talk. Okay. So here's the magic formula. It might look exotic when you first see it, but I promise you this is how you will be computing this little e and this capital E matrix here. So there's a bunch of data here you've already seen before. It's the probability of the scenario. It's the TK is just, this piece of data here. So we know that when we're starting the problem. What we don't know are these pi's, and you ask, what are these pi's? These pi's are the dual multipliers of the second stage linear program for a certain trial decision xv. Okay. You tell me, what do you want to do in the first stage? Give me an xv. a candidate. I'll plug it into the second stage optimization. I will solve this problem for each scenario. You can see how you can solve this problem independently, right, for each scenario. And each different scenario will produce a dual multiplier. Here, simplex will report it back to you. You store it in memory, and then you go back to the and apply this magic formula here, and that will give you exactly these lines here. Now, that's the trick. Now I'll spend the rest of the course trying to convince you why these are the formulas you want to apply. Okay. Now, I've already given you enough information to help you understand how an algorithm like this would evolve. Suppose that I had that my first stage cost is 0, and suppose that this is my value function in the second stage, and suppose that I have a first stage constraint that says x between 0 and 10. Graphically, how would this algorithm evolve? And I'm also going to tell you that we will be starting from x equals 0. So x equals 0 is here, x equals 10 is here. Graphically, what would happen? I'm giving you the first candidate. It's 0. What would... so the way this thing is going to evolve is I give you a candidate, you solve the second stage optimization, you come up with a cutting plane like this that exactly supports the value function, and then you go back to the first stage and optimize as if your value function were this line here. What would be the minimum in that case? It would hit 10, so this would be your second iterative. This would be x1. And then what would happen here is, again, I would send this to the second stage. It would identify this line here as the second cut. It would generate it. And then after generating the full picture, in the third, it's going to solve this master problem again. And in the third iteration, it's going to indeed detect the minimum. In one dimension, this looks lovely, right? All you're doing is ignoring the fact that this is piecewise linear and solving as if it's something simpler. In multiple dimensions, you can see how this can take a lot of back and forth communication. But this is the idea of how this works. Is this clear? Okay. Don't look troubled.
Yes.
Okay, let's see the graphical version again. So we have a master. Master produces an X candidate. Second stage returns back a cut, which is an E matrix and an E parameter. These two things describe this line here. The specific line they're going to describe is the exact support of the piecewise linear function. The exact support of the piecewise linear value function at this point here is this line. So if I give you as a candidate the value 0, you're going to give back to me this line here. If I give you as candidate the value 1, you're going to give me back the same line. Just think of this as an oracle, like a magic box that returns back this piece of information. And the oracle, all it does in fact is this. If I started from here, the line I would have returned to the user would have been the support of the value function at this point here. But the bottom line is that as I'm building gradually this function, I'm moving around in the X space, asking for different cuts, getting them back, and getting a better and better, more accurate description of the value function until I hit them. Okay. that's the algorithm. So now let's see why this works. Okay, here's a drawing of what I could have avoided getting my sweater all white, but it's okay. So this is what happens. Trial x, this is the piecewise linear value function. You tell me what x you would like to consider. I tell you what the line that defines the value function at that point is. Okay. And here's how you implement this in code. You have 3 counters. This R counter is the one I want you to focus on right now, which is how many of these lines you've generated. When you're starting the algorithm, this counter is 0. You don't have any description of the value function. You solve this master problem, which is only solving for x, but it's ignoring the true multi-cut version of the value function. It has a simplification, and we call it the master problem. If you remember, this master problem has 2 variables. It has the x and the theta, so it's going to return back an optimal x and an optimal theta. If it happens that this is the first time if you're just initiating the algorithm, you define the first theta as minus infinity. So your original, since you don't have any lines describing the value function, you're taking it as the least value possible. Then you store the x, you send it, you check if this x is feasible, and we'll talk about this more later. If it is feasible for the second stage, you compute these pieces of data here that help you define cuts. Now I've told you how you define these optimality cuts. One thing I didn't talk about was your termination criterion. It will turn out that to terminate, you need to compare the theta you computed in the master stage here with WV. What is WV? It's the new cut you generated evaluated at the x you just calculated. If it turns out that the theta you computed here is greater than or equal to this value here, you should stop. And I'll explain to you why you should stop. Okay? This is the algorithm. And if it's not the case, then you go back to step 1 and bounce between step 1 and step 3, provided you're always generating feasible decisions. Okay. Yes?
Why is theta v always
Why is theta v always optimal?
Yes, because we wonder if theta v is bigger than WV.
Yes.
So, and why is this a criterion?
Why is this a stopping criterion? Good question. That is something that I need to tell you a couple of things before explaining why that's the case. So we will see that around around the last quarter of the presentation. I need to give you some background information first before I can convince you that this is the stopping criterion. Okay, so the first, okay, let's see how optimality cuts are generated in a specific numerical example. And this is our stochastic program here. So we have 2 first stage decisions, x1 and x2. And we have randomness showing up in 4 parts of the problem. The coefficients of the second stage, and the right-hand sides of these second stage constraints. Okay, so our random vector, it consists of 4 pieces of data. And we have 2 scenarios, 40% for scenario 1 and 60% for scenario 2, and this is the data. Now, I'm using this notation K2 here, and I'm setting this K2 equal to R2. I have defined K2, I have defined K2 over here, right? What is K2? Can you describe this in English or French? can you translate this into something that looks less mathematical and more intuitive? Is the collection of x's, the collection of first stage decisions, such that I can find the second stage decision that can satisfy the second stage constraints? Is it worth considering x's that are outside K2? It cannot do the job, right? By the definition of K2, these aren't feasible solutions for my problem. Because there will be maybe more scenarios that will make this impossible to satisfy. That's one bunch of constraints I need to respect for the first stage problem. The other bunch of constraints I need to respect are the AX equals B constraints, which I will refer to as a set K1. So the set of x's that satisfies this is K1. Okay. So my claim in this problem here is that K2 is the universe. K2 equals R2 means I'm claiming that you can pick any x you like, and there will be a second stage reaction that will make the problem feasible. Do you believe that or not? For this problem. Leopold, do you believe? Are you a believer?
Because matrix 6, 10, 8, 5 is full rank, something like that. So you can pick up any x you want.
6, 10, 8, 5 is full rank. I also have, okay, you're saying 6, 10, 8, 5 is full rank.
Oh, yes. And the y has to be positive, but it doesn't matter.
So you're saying we can span all of our two? Yeah, that's pretty convincing, I think. But I'm wondering, well, we can span all of R2, but y is constrained to be non-negative, right? So that's a tricky, that's a good thought, but if only y were free, it's not. It's also non-negative. But I'm gonna say here's a specific y that will always do the job. So try y equal to 0 and 0. Do I satisfy these constraints here? I satisfy them. Negative, but I know that it cannot be. Okay, so provided that x is in K1, which is the first stage bunch of decisions, I know it's going to be non-negative. And so how about here? We know also that the data for both scenarios is greater than or equal to 0. So no matter what you do with your x decision, here's a feasible second stage one, y equals 0, 0. So that means you have the freedom to choose any x you like, basically, which is why this K2 equals R2 holds. You buy that? Okay. So how would you commence the algorithm based on step 0? Well, step 0, you set the counters to 0. Step 1, what do you do in this specific problem? So solve master problem. It's maybe hard to remember what the master problem is, but in words, the master problem is ignoring everything that could happen in the second stage and only paying attention to first stage cost, first stage constraints. So what would the master problem look like here?
Midpoint 100x1 plus 100x2.
Yes.
So that difference with x2 is less than 120.
You need more. Come again?
And x1 to be greater than 40 and x2 greater than 20.
Right. And in general, in every step except for step 0, you would also add a plus theta in the objective function, but not in the first iteration. In the first iteration, you ignore the theta, you by default set it to minus infinity. Okay, you solve that problem, which is, remind me of your name, I apologize. One more time, can you remind me of your name?
Daniel.
Damien, yes. So Damien just described the problem here. If you solve this, I think we can all see that we're trying to push x as low as possible. We're going to pick 40 and 20 as the optimal solution of this. I mean, it's a good idea if this were the real problem, but what you're doing here is you're ignoring the impact you have on second stage costs, which we're going to start building up that description now. So this is the x1, this is the theta 1. We set it by default to minus infinity, and then we move to the second stage. Okay. Second stage for scenario 1, we have, if you recall, the costs are minus 24 and minus 28 for scenario 1, and the d's are 500 and 100. So minus 24 and minus 28, and 500 and 100. Where did these right-hand sides come from? Remember that I'm now trying out a specific x. So the right-hand side coefficients are 60x1, 80x2. My specific x is the one I computed in step 1. So I'm going to plug in 40 and 20 here, and I'm going to get 60 times 40 is 2400, and 1600 is from this. Is that clear? Okay. I solved this, and it evaluates to this is the objective function value, this is the second stage optimal solution. We could, I mean, okay, interesting, but we could throw all that away. What we really want to keep is, this is the crop out of the harvesting. We want to keep this. Similarly, for second scenario, the only thing that changes here is the coefficients. Oh, maybe there's a typo here, sorry about that. These should be the second scenario coefficients, which are minus 28, minus 32. Sorry, I will correct that. And then we have the second scenario right-hand sides. The 2400 and 1600 don't change because it's the same trial decision. Yeah?
Yeah, so I just have a question about the sign of your multipliers.
Yeah.
What is the convention? Because here they are negative, so it will be positive. I mean, how do you take your constraints? You mean for the cuts or for the constraints of the original problem? Yeah, I mean, those multipliers, suppose that you take your constraint in the, like,
if I change the signs of the inequality, the sides of the inequalities, is that what you're?
Aren't you like? Yeah, that's it.
You're going
on the way you look at it, the sides are different.
Correct. That's a good point. So you're going to see in the book a generic version of the problem, which is tx plus wy equals h. And that's not what I showed you here, right? Here I'm giving you inequalities, less than or equals, greater than or equals. I'm playing around with this. I'm kind of relaxing this. Same recipe applies. Now, if you had, so for example here, if this were minus the left-hand side greater than or equal to minus the 60, the dual multiplier would have an opposite sign in the software. But the same recipe applies. You can demonstrate that theoretically, that no matter what side inequalities are, you just apply the same formula over here for computing the cuts. It works in any case. Is that what you asked?
Yeah, it's okay just because, so I've done that in MATLAB, but aesthetically it's like with the left expert, you can show them just after when it looks like. The problem is that every time I do that, I try once with one side and then it's wrong, and then I put a minus and then it works. But what is the convention? Should we then always positive or always negative?
I'm a bit surprised. Are you sure? So MATLAB is reporting dual optimal simplex multipliers or sensitivities?
No, perhaps there's this problem in science, but I felt like there were dual variables.
We should look into this.
Yeah, I'm sure you just have to.
Yeah, no, that's a good point though. For implementation, it matters. Okay. Yes.
So the simplex multiplier are the
Come again.
what's the simplex multiplier?
The simplex multiplier is the multipliers that solve the KKT system of the linear program. It's the usual ones you've seen in linear programming. And these can be equal to or minus the sensitivity of the objective function. Some software reports sensitivity. Some software reports the solution of the KKT system, and these two things can be different. They can have the same sign or the opposite sign.
Okay, but the absolute value is the same.
The absolute value is the same.
Okay.
Yeah. And what I'm referring to here are the dual multipliers of simplex. Not necessarily the sensitivities, but the dual multipliers of simplex. Okay. Okay. So we solve the second stage. Also, we get the pi's for the second stage. Now we're ready to build our cut. So here's how you compute the cut. So let me write out these things so you can remember them. Okay, so here is the data we need to compute the cut. H1 is 0, 0, 500, 100. If you remember, H1 is the right-hand side of the second stage constraint. So my question to you is, why is H1 not 2,400, 1,600, and 500, 100? Instead, there's 0 here and 0 here for H1.
Because this is W units.
Come again?
This is W units.
Yes, exactly. So when you're looking at the problem here, it might look as if this is data for the right-hand side, but not in the original formulation. In the original formulation, this is Wx. Okay, so it influences the pi you're going to get here, but that's not your h vector. Your h vector is the one you had in the original statement of the problem, which is this one over here. Okay, so we have that. We compute E1 by taking the weighted average of the pi 1 with h1 over here and the pi 2 with h2 over here. By weighted average, we're weighing by the probability of occurrence of the scenario. Scenario 1 has a chance of 40% of occurring, so we take its inner product with h1. Scenario 2 has 60%, and we take this inner product here. So when you do pi 1 transpose with h1, you have 0, 0, 500, 100. So 0, 0, 0, and minus 13 times 100. And then, yeah, that's the minus 1300 here. So you do also the other inner product, and you do minus 520. That's your little e parameter. Similarly for the coefficient matrix. And so here the t, the notation here is the first column of t is minus 60, 0, 0, 0. So if you go back, the t, what you should be thinking is where are my x's? So my x's in this problem are on the left-hand side. So the minus 60 is coming from here, and the minus 80 is coming from here. That's how you get the T1 and the T2. So this is how you get the cut that you need, okay? And how do we use this piece of information here, the W1? Do you remember from the statement of the algorithm? What was our termination criterion? So how are we using, why are we even bothering to compute W1? Theta 1, right. Is there any chance that theta 1 will be greater than or equal to W1? We've set it pretty low. So we have the cut, it's minus 520. This is the coefficient vector, so this is the W1 for the trial X, which is 2040. And we get this number here. We find that it's bigger than minus infinity, and a huge surprise. And we add this cut to the problem. Okay, so here's how you come up with these magic numbers that define the value function. Master problem round 2. Damien, you want to enrich the statement of the problem that you described earlier? Damien? Do you want to... You told me what the master problem was before. How would you change it now that you have this optionality?
We have to add theta to the objective function
and this constraint. Exactly. So here's our master. New trial decision, 4080. New theta is this. We go through this whole process again. New cut is this. Iteration 3. So we're getting somewhere, right? We're moving around the x's. Iteration 3, new trial, new theta, new cut. Iteration 4, new trial x, new theta, new cut. Iteration 5, this is the master by that point. This is the theta 5. And when we compute the cut for that iteration, it turns out that it's equal to theta 5. And we're done. So here's an example of L-shaped in action. I haven't still told you why the theory works. And before I jump into that, let me talk you through another example that's much more geometrical. And we can take a break and then we can see the theory in the second part. So this problem here, my claim for this problem is that the second stage cost is psi minus x. So do you see what's going on here? We have two non-negative y's, and they're basically slack variables for making them equal to psi minus x. If psi minus x is positive, then the optimal solution is what? What should like to be? 0, 0 won't work. Psi minus x and 0. And the other way around. If this is negative, the y2 is positive, the y1 becomes 0. So basically, the second stage costs, because then we're going to add these guys up, it's just like taking the absolute value of the psi minus x here. Okay, 3 scenarios equally likely, 1, 2, and 4. And K2 again is R. So no, you can pick any x you like. I will find y's that will satisfy the constraint. If you go through the L-shaped algorithm, starting from 0, you generate first this cut here, and I'm going to draw this for you. So x1 over here, and first cut 7/3 minus x, and x1 extends to 10. So this is my first optimal cut. When I'm minimizing in the second iteration this problem here, I'm going to very naturally move to this optimal solution, x2. Indeed, x2 is 10. And I'm going to generate the following cut, x minus 7/3. It's like the mirror of the first cut. Okay, second trial decision. X to 10. I want to say that this cannot be. I want to say that this should be 5. Because these two are symmetric, so. Huh. 7/3. I may have made a typo here, but I would expect this to be 5. Do you see why I'm saying that? You have symmetric cuts here, and you're playing between 0 and 10. Anyway, I'll check the book for that.
The symmetric around the x-axis, not really around 5.
They have the same. You are right. Yes.
No, it's 7/4.
You are correct. Very correct. Yes. This actually hits here. Yeah. Sorry about that. It's minus 7/3, so it would be somewhere here. Right. And it would have the same slope, but it would meet with this. So what I want to draw, something maybe like this over here. Okay, good point. Thank you. Okay, so we above 0, above below at 0. Yes. Yes. Okay, so. Okay, so second candidate third candidate x3. New optimality cut over here is this guy, so a third plus x third, maybe something like this. Oh my god. Something that would look like this, perhaps. Then new minimum over here, x4. And then this is equal to a 1.5, new cut. And if I continue drawing, it'll just be a white blur on the board. So I will just give you the graphical version already. So we already drew these on the board. So first cut over here, second cut over here, and third trial over here, and that's how this thing evolves. And like Leopold pointed out, yeah, these two intersect at 0. Okay, so the book points out to the reader that, what a coincidence. Your value function, if you look at explicitly at this formula and you go through the numbers by hand, at x1 is 7/3, and around x1 it's 7/3 minus x. And then the book also explicitly points out that, oh, what a coincidence, that happened to be the first optimality that you got. So then it starts getting into why actually these formulas that I showed to you earlier give us the exact support of the value function. This, in yellow alarm signs for the fans, this is for me a very helpful way to remember geometrically why the L-shaped algorithm works, and it's indirectly a proof of why the value function is piecewise linear. Okay. Here's what happens when we're solving the second stage problem. We have this Q function of first stage decisions and uncertainty. This is the linear program we're solving, and the dual optimal multipliers are these over here. Did you buy this? Have you seen this formula before for dual optimal multipliers? This is the, we covered this theory also when we were doing the linear programming theory in lecture 2. You can remember this as the recipe of computing dual optimal multipliers. You tell me the optimal basis, the dual optimal multipliers are the coefficients of the basic variables transpose times B inverse. Okay, you can refer back to the theory to confirm this. So from duality, we know that if we take the dual optimal multipliers of this problem and hit them with the right-hand side, we're going to get the same value as the optimal solution of the problem. So dual optimal multipliers multiplying the right-hand side of the problem is exactly the second stage cost for that scenario. Okay. So what is a check for whether a basis is optimal or not? And this is also one of the things we covered in lecture 2. So remember that when I give you a candidate basis, you should be computing a couple of things. You want to make sure that the B inverse B, which are your basic variables, is not negative. If I give you a B here that's invertible, but one of its elements is negative, it can't be, it's a basis, but it can't be it's not even a feasible basis. So any eligible bachelor should at least satisfy this checkpoint here. Now, really, the one B that you really want to pick up also has to be such that the non-basic variables, the candidates for entering the basic solution, when we're minimizing those guys, when we describe the Z as a function of non-basic variables, it's basically some linear function of the non-basic variables. The coefficients of the xn's must be greater than or equal to 0 if that basis is going to be optimal. Because if there is one coefficient of the non-basic variables that is negative, then that guy can go in and improve the objective function value. This is Chinese. I can write this out in a more analytical way for you if you're getting lost, because it's really helpful to understand this. Let me write it in a more analytical way. Okay. So we have this is our optimization problem. This is the AX equals B matrix broken into its basic and non-basic parts. And these are the non-negativity constraints. Okay, when we have a candidate basis, these guys are all 0. So all we're paying attention to is that the bx b equals b and xb non-negative system is satisfied, which means that what we really want is b inverse b to be non-negative. Check. Here's the tricky part now. What the pivots in the simplex algorithm are doing is the following. They're saying, okay, you claim that this is the optimal basis. Well, let's express the xb as a function of the non-basic variables using this equality here. So what the pivot algorithm is doing is basically one of the rows, if you remember in the pivot algorithm, is the row for z. And it creates coefficients for the non-basic variables there. The way it creates them is like this. Let's try and express the non-basic variables as functions of the basic ones. The basic variables as functions of the non-basic ones. For this basis, this system has to be satisfied. So then if I plug in this into the objective function, I want to make sure that the resulting coefficients of the xn's can't improve my objective function. If that's the case, then I have an optimal basis. Makes intuitive sense. Okay, so if I plug the xb over here, what I get is basically CB transpose B inverse, B minus nxn, plus Cn transpose xn. Which, when I isolate the xn, is CB transpose B inverse B, oops, sorry, this is a constant term, plus Cn transpose minus CB transpose B inverse, and xn. This, we want to make sure, is for this basis greater than or equal to 0. If that's the case, then the basis is optimal. And again, the logic is fairly simple. You claim this is an optimal basis. Okay, for that basis, I can express the basic variables as an affine function of the non-basic ones. I can plug them back into the objective function. So if your claim is that this is the optimal basis, then when I substitute the basic variables for the non-basic ones, if I can find an improvement, you lied to me. That can't be basic solution. That's the geometric intuition of what's going on. But you've seen these formulas here in linear programming. This is the reduced cost of the non-basic variables, which is what the simplex algorithm checks to test optimality. This is exactly the reduced cost. Okay, so back to the slide. I'm finding the pointer. Okay, so when I'm now looking at this linear program, this linear program, the b vector in this linear program is h minus tx. So when I'm, suppose I found an optimal basis for this linear program for a certain trial x. I argue that it will be the optimal basis even a little bit around that trial x. How would you check for that? What changes as I'm changing the x? A bit in this linear program over here. The right hand side. So there's these two checks that we need to make for an optimal basis. One is B inverse B greater than or equal to 0. The other is Cn transpose minus Cb transpose B inverse n less than, greater than or equal to 0. These are the two things that need to be satisfied by an optimal basis. In our situation here, the B is basically h minus tx. These guys are not influenced by the x. No matter how you change the x, this part of the check will not change. As long as I'm claiming this is the optimal basis, the only thing that's changing is this. So if for a certain x, the pi is optimal, it's going to be optimal no matter how much you move around the x, as long as this set of inequalities holds. So it's not, a value function is basically, the cube basically has this expression here, not only at the specific x that generated the pi's, but in a neighborhood, in this neighborhood here. What is this, basically, geometrically speaking? This thing has a specific shape, geometrically, as a function of x.
Plane.
It's a plane. So I know that the Q for a certain neighborhood of X looks like a plane. If I move the X too much, then these inequalities are violated and I have to look for a new basis. When I find a new basis, I present it to you, and again, I play the same argument to tell you that if you move around that X, still the Q is a plane around that X. So basically what I get is that Q as a function of X is piecewise linear. Okay? It's always like a plane, but the slope and the intercept of the plane change as I'm moving around in X. That's the geometric claim of why Q is piecewise linear, and then all V is an average of Q over scenario. So V is also piecewise linear. That's the geometric version of the problem. So what I told to you is, basically in these pointers here, that B is an optimal basis as long as its two criteria are satisfied. So this second criterion here is basically this stuff, but written for this specific linear program. Okay, in our specific linear program, the non-basic, right, this is this one is obvious, B inverse H minus Tx. And this one is basically the reduced cost criterion for the following reason. I want to rewrite this. I'll double check on how we come up with this specific, but the takeaway from here is it doesn't depend on X. That's the important thing. So Q has this geometric expression as long as these inequalities are satisfied. So then this is the value function, just the expectation over a bunch of piecewise linear functions. And it looks like this. It's an affine function of this in this set. But when we move to a different set where this is not satisfied anymore, we can find another optimal basis. And the V will again look like this. It's just that it's going to be for a different basis. Okay, and if the Q's are affine functions of X, taking an average, which is the V, doesn't change the geometric description of the problem. That's still an affine function of X. Okay, and this basically is an indirect proof of why the formula I described to you earlier is the formula that will do the job. The V I just argued to you is exactly equal to this. Well, these are the formulas we use for computing the little e vector and the capital E vector. Okay, feasibility cuts. So we've seen how to build this value function incrementally. What I'm going to show you now, and what I haven't discussed with you, is what happens if what you choose for the first stage turns out to be infeasible for the second stage. And we again will apply the same idea of solving a bunch of second stage problems and sending back some information to the first stage. What is this problem doing here? F. The E's are unit vectors. And the I's are identity matrices. Any thoughts? What it looks a lot like some problem, but not quite. In the constraints, at least, it reminds you of. this should give you the hint that this looks like the second stage problem. Maybe the notation is not clear. So if I were to write this out, for example, for a two-dimensional problem, actually here's an example. Here's an example of this model formulation for this specific problem. So here we have two first stage decisions. This is the second stage cost, and these are the constraints. So one second stage constraint, second stage constraint, and two more over here. And we formulate, there are 4 scenarios, and we're going to pay attention to this one. The scenario where Xi1 is 6 and Xi2 is 8. And I'm going to give you a trial decision, X, which is 0, 0. And I'm going to formulate this problem here. So what am I doing in this problem here? I've got a bunch of V's, pluses and minuses, and I've changed all of the constraints of the problem in the second stage. When I'm doing this in a constraint, what am I basically allowing myself to do? Adding and subtracting 2 different non-negative variables. What am I allowing myself to do? You can cover any value you like in the right-hand side. So the V plus and V minus are helping me go up and down that constraint as far as I like. Now, I'm also adding these constraints in the objective function. And the other thing I want to say is the plus indicates that's the variable I used to go up, and the minus indicates that's the variable I used to go down. I'm also adding these in the objective function. So what could you tell me about this? What could you tell me about this problem if this objective function is positive? Exactly. This is a phase 1 of simplex, basically. We are using our auxiliary non-negative variables to add slack to the constraints. And if I can't make my objective function value 0 for this augmented problem, then I can't satisfy these constraints really. I need these artificial variables to move around in the constraint set. This notation, so here this is basically the notation I've used here. These are unit vectors, so E is basically this. Well, it's a bunch of 1s. So I'm adding up all the V pluses, I'm adding up all the V minuses, and the adding and subtracting V pluses and V minuses in the constraints are these things here. Okay, so the idea with the feasibility cuts is that when you are trying out different x's and sending them to the second stage problem for generating optimality cuts, before you do that, make sure that these are even feasible x's. Because if for some scenario this is not a feasible x, then there is no optimality cut to calculate. It's an infeasible problem for some scenario. Makes sense? If you plug this, if this is an infeasible x and you plug it into the second stage and you're looking for the pi's, that's not even going to solve. Simplex is going to come back to you and say infeasibility, no dual multipliers. Okay, so you need to check that this is a feasible x. And the way you do that is you go one by one through all of the scenarios, solve this problem. If the objective function value is 0 for all of them, then you know that you can satisfy the constraints for all of them. But if it turns out that for one of them, the objective function value is positive, then you're in trouble. For that scenario, you're infeasible, and you need to generate an inequality that you send to the first stage to prevent that from happening again. And the inequality you generate is generated like this. You solve this problem here. You get dual multipliers for these constraints, and you hit them, and you create these matrices here. You left multiply tk for that scenario by the dual optimal multipliers. You left multiply the hk by the optimal multipliers, and you form an inequality like this: dx greater than or equal to d. That's again the magic recipe, and I'll justify why this is the idea. So back to the example. For a trial x which is 0, 0, and for this specific scenario, if we solve this problem, we do get a positive value of the feasibility problem, which means that for this specific scenario, the x is cannot lead to infeasibilities. Now, if we then ask our favorite linear programming solver what are the dual optimal multipliers, we get back a response like this. And we generate the the feasibility cuts by looking at what is my H vector, what is my T matrix, and I apply the formula that I showed you earlier. I get this coefficient matrix here, and this right-hand side right here. So this is my coefficients for x1 and x2. So 311 is x1, 111 is x2. This is my right-hand side. I put that here. I can now promise to you that if you plug this cut into the master problem, this 0, 0, 0 shall never reappear again. You can check it. What happens when I have this constraint if I use 0, 0? It violates this inequality. So I showed you a recipe. Again, I haven't told you why it works, but it will cut off this candidate. What you want to avoid when you're doing that. And this is, I just put an inequality in the master problem. It changes the feasibility region of the first stage problem. So let's make a drawing here. Again, K1 is the set of x's that satisfy the first stage linear constraints. K2 is the set of x's such that I can find a feasible second stage reaction. These two, you can think of them as polyhedra in Rn1. Okay, when we're looking at Rn1, K1 could look something like this. K2 could look something like this. And what is for us the feasible region of the problem is the intersection of these two guys. Any x that does not live in this shaded region is not of interest to us, it's useless. And what I just did now is I generated a half space here. So I had an xv. Could that xv be over here? No, other question. Could it be here? The xv. Where did this xv come from? It came from a master problem. So, Camineto?
Have to be.
Sorry, I didn't get you.
Easily have to be in K1.
Yes, exactly. So it can't be here. So it has to be in this space here. So if it's over here, well, if it's over here, then we're good. We can move to step 3 of the L shape, no problem. But it might be over here. So I just generated here a half space that I will add this half space to my master problem. Let's suppose that I generate this half space over here. Sorry. This is in fact, sorry. So, will this half space do the job? Is it a good half space? So, is this something I want to send to my master problem? First of all, does it cut out XV? It's XV is sitting on the other side, so if I plug XV here, it will violate these constraints. What is it doing though that we don't like? It's exactly. We want to give these guys an opportunity to be considered for optimality. We don't want, by generating this cut, to throw out any pieces of K2. So I definitely want to make sure that this line cuts off XV, but at the same time, all of K2 is sitting on the other side. There's a theorem in convex analysis that says that geometrically, I can always find such a line. I have two convex sets, there's always some line that can separate them, have them on different sides, separating hyperplane theorem. How I come up with it is through this, you guys are shaking your heads like you've been burnt from this in the past. How I come up with it is by applying this recipe here, which for the moment looks like it's coming out of nowhere, but we'll see why it works. Okay, so by doing this recipe here, I can guarantee to you that this is the cut you get. That's feasibility cuts. Okay. So I'm going to show you how these apply for the problem that we have. So starting from x1, it was 0, 0. We got the cut over here. We plug it into the master. We go back. We get this guy here. It's looking better, right? The x's are increasing and we need that. We get a second feasibility cut applying the same recipe. We go back. We get a third candidate, third cut, applying the same recipe. We go back, we run the master, we get this. Turns out that this is feasible. I've just done 4 up and downs to get just the feasible point. Just looking at the problem, do you think you could have avoided all of that stuff? Could you have been a bit smart about writing out the master problem to add some extra information to the master, make the x's it's generating look more likely to be feasible? You have x's that are lower bounded by stuff. So they know that they have to be always at least something. And this stuff is y1 and y2, and it is also lower bounded by xi1 and xi2. So what's the worst xi that could be materialized here? The one that makes the tightest feasible region. I want to say Elaine, but I think I'm completely massacring. Can you remind me of the name? It's not Elaine or Eleanor. Not even close. Estelle. Okay, Estelle. sterling thoughts about what's the worst xi? So you're saying 4-4. Come again?
6-8.
We have a disagreement.
For which variable works?
Who votes for? Sorry?
For which variable the state that we have to choose 6 line to have the highest region for x?
For x.
Also, it's the smallest.
The smallest xi? So who votes for the smallest?
For x, the biggest.
The biggest. Raphael? Convinced?
No, I was thinking for y.
Again, we're thinking of how to make the master problem smart. So you know you're going to run into this 6-8 eventually. You want to make sure that you preempt it by putting it in the master. So 6-8 looks pretty bad. And in fact, if you have 6-8, what you get is y1 has to be at least 4.8, y2 has to be at least 6.4, and then you plug those values into here, you get two lower bounds, one for x1, one for x2. Turns out, if you had done that in the first place, so this is what I just said, if you had done this in the first place, you could have avoided all of this stuff. Sometimes you really, before blindly applying the cookbook, you need to think about your problem first. In my experience, feasibility cuts are great theoretically. They prove the convergence of L-shaped method. In practice, they are useless. I've had problems where I've spent 2 days on a machine running and just generating feasibility cuts, and it never even starts generating optimality cuts. So in real problems, you really have to look at the problem. Again, there's theoretical value because you know it guarantees finite convergence of the algorithm, but in practice, it's not the best thing you can do. Okay, so back to this drawing over here, and then the book discusses what are situations where you can avoid generating feasibility cuts. So one situation where you can avoid feasibility cuts is complete recourse. The definition of complete recourse is that the positive, I don't know what's the official name of this set, the positive span of W is Rm2. What does this mean in English? So what is this set here? It's this guy over here. So this set is, if I am adding up the columns of W with non-negative weights, what space in R2 can I span? What does it mean if this set here is equal to Rm2? The second stage constraints of my problem look like this. So I'm now looking at how much space in the universe I can cover with this vector here. If the columns of W are rich enough that I can cover all of Rm2, I don't care what you give me here. I can always get to it by playing with this vector. It's a very powerful assumption. That assumption is called complete recourse, and it's just saying that no matter what you do with your first stage decision, I can always find a Y to make it happen. This is a bit different from relative complete recourse over here. The drawing for relative complete recourse is something like this. It's this drawing here, but oh no, the other way around. Yeah, it's something like this. So K1 is contained in K2. That means if I pick a K1, an X in K1, I know I'm also in K2. So relative complete recourse means if I satisfy first stage constraints, definitely also satisfy second stage constraints. In these two situations, I don't need feasibility cuts, right? In the first case, because any X will do. In the second stage, because if I satisfy K1, I satisfy K2. Okay. I wonder if I should attempt that now. Yeah, let's start it now. Probably, Matthew, I'm going to use some of your time on Friday. Okay, so proof of convergence. Okay. I'm going to make, okay, to prove convergence of the L-shaped method, you want to observe two things. When you're the master, you get a theta v, and you also get an xv. That's the two pieces of output you get from the master. And there's a value function at xv. It's you don't know what it is, but it is a specific number, and two things could be happening. Either the theta v you get is greater than or equal to that v of xv, or it's less. Even if you don't know what this is yet, one of the two things has to happen. And I'm going to claim that by the end of the iteration, you will know. When you're solving the master, you don't know what the v of xv is, but by the end of the step 3, you will know what it is. Now, what I'm going to try and prove to you is that this condition, first of all, implies optimality, and second of all, the termination criterion I gave you when I was showing you the L-shaped method is comparing theta v with a wv, if you remember. Well, that wv I'm going to show you is actually v of xv. So I'm going to show you those two things, that this implies optimality and that v of xv is equal to wv. And I'm also going to show you that this case over here can only happen a finite number of times. So this has to eventually stop. When we're going back to the master, it's going to happen once, twice, 3 times, but eventually it will. It can't go on forever. Okay, these are the things I want to argue. So the first, I'll start by arguing that the wv that I mentioned in the description of the L-shaped method is the value function estimated at xv. If you recall what this wv is E of the U cut evaluated at xv. Now, when we did the second example, you saw that there was this value function that looked something like this, and we started at 0. And the first cut we came up with was this here. So what I want to show, and by the end of that iteration, we calculated the W1 here. So graphically, we saw this happening in the second example. Not only did we know that the W1 we computed here was equal to the value function at that point, but we also had an exact support around that, right? So let's see the proof of this. We've already seen this graphically. Let's now see formally why it holds. Okay, so from linear programming duality, we get from our solver the dual optimal multipliers of these constraints. We know that if we take the inner product for a certain trial decision xv of the right-hand side and the dual optimal multipliers, we get the objective function value. Okay, so we know this holds over here. And if I take expectations with respect to all of the scenarios, that's by definition the value function at that xp. Well, if I do taking expectations means on the right-hand side, I'm summing up these guys multiplied by their probability of occurrence. And these formulas here should look familiar to you. These are exactly the little e and the big E we computed for that iteration. Well, for this specific x. So this value is this thing over here for the specific x, xv. So this is in fact actually the WV that we encountered in the termination criteria. Again, the WV was this thing when you see the description of the L-shaped method. When you start in step 1, you don't know this vector and this matrix. But by the end of step 3, you know them. So then once you know them, if you plug in the xv, that's exactly the value function for that point. Okay. And that's why before, when we computed a cut here, it wasn't just any line. It wasn't a line that was above the value function. It wasn't a line that was below the value function. It was a line that was exactly on the value function. Okay. So first piece of information, the WV we get at step 3 is the value function at that point. Very important fact. Second fact is that if this holds, if the number I get from my master is greater than or equal to that WV, I'm optimal. I have to be optimal. I claim that, and I'm going to try and convince you it's true. To prove that, we take advantage of the structure of the value function. You've kind of seen this in the homework already. Well, I've told it to you in a way. I've told you that V is the value function is a piecewise linear function. That means it's basically a convex function. And you've definitely seen this in your homework. The dual multipliers are basically the subgradients of this function. Okay, that means that if I so basically that said, here all I'm doing is applying the subgradient inequality. I know this is the slope of my function at a point xv. If I move on this hyperplane away from xv, that line is underestimating the true value function. So I know that for xv there is an equality, but if I move away from xv, the line is underneath the cube. Okay. So then when I take expectations here, I know that for the entire value function, the same thing holds. And that's an important fact now, because when I look at my full problem, an equivalent way to write it is this. Here I'm not, I'm just writing the full problem without dropping any constraints. So I argued to you earlier at the beginning of the course that this formulation describes a piecewise linear function. So if I know that v of x is piecewise linear, this is really the original problem I want to solve. And what I notice is that the master problem is almost this. It's not exactly this. It's just a bunch of other things in the right-hand side, on this side here, that are underestimators of v of x. So basically what the master problem is a relaxation of this problem here. For example, again, graphically speaking, when I'm solving this optimization problem here, for these two lines, the yellow lines, it is a relaxation of the real optimization problem, which is solving for the white line. Because I'm ignoring a bunch of these lines, over here, and I know that the yellow ones will be underneath the white ones in this space over here. So the master problem is a relaxation of the proper problem, and the claim goes as follows. I've just argued that the master is a relaxation of the real thing. And suppose that when I'm solving a relaxation of the real thing, I find an xv and a theta v that satisfy the determination criterion constraint. That theta v is greater than or equal to wv. Then what I want to argue is that there will be no competing x that can solve the problem better. So to argue that, what I want to say is that, okay, you say that xv is not the optimal solution of the full problem. Present to me a competing x bar. If the competing x bar you claim is optimal for the real full problem, then when I plug it into here, I have to do better than xv, because this is the full problem. Well, if I'm going to do better in this problem here with your competing candidate x bar, then I have to also do better in the relaxation, which is the master problem. If the x bar is the best possible solution for this problem here, which means that it does better than the current xv, when I'm also solving the master problem, which is a relaxation of this, I would have gotten x bar, not xv. So there's a contradiction there. The reason being that the master is a relaxation of the full problem. Intuitively, what happens is this is going to be theta v, and in every iteration, theta v is the minimum of the intersection of the yellow lines here. Well, actually, no, this is the proper way to draw it. I'm hoping I'm not getting completely lost at this point. But the way to think of this geometrically is the following. At every iteration, for example, at iteration 2, the theta v is the lowest point of the relaxation. The wv is the actual value of the value function at that iteration. If these two things hit each other, then I'm done. I'm optimal. That's the geometric way to think of the L-shaped method. Theta v is the lowest point of the relaxation. wv is the real lowest point. So what happens in step 1 is I get what I think is the optimal value if the yellow lines were really my value function. By the end of step 3, so that's an illusion basically of what is really going on, but by the end of step 3, I really know what the value function is. It's wv. If these two things are squished on each other, then I'm optimal. That's the geometric way to understand this. And the last thing I want to say today about this, so I argued to you that first of all, my termination criterion is equivalent to this condition, and this condition implies optimality, so my termination criterion is correct. And the second thing to observe is that this check over here, this part will happen only finitely many times. So as I'm building these lines, this distance will be positive only finitely many times. I'm going to be eventually closing this. The gap might not be decreasing at each step, but it's eventually going to close. Okay, so to to see that, you basically want to be thinking of what does it take for this condition to occur. So here's a question for you. Is it possible, as I'm running step 3 of the L-shaped method, that I return exactly the same multipliers that I got in a previous iteration of the same algorithm? Is it possible? If I were to get the same multipliers, what would the optimality cut look like? It would be identical. So if I, again, thinking geometrically here, if I violated at the current iteration, I have a theta v which is here, and the WV which is here, but I already had that optimality cut in my master, that couldn't happen. I can't, by the end of step 3, get back the same answer about all the dual models. Some might be the same, but all of them cannot. Because if they are, then I would have seen that already in the master problem. That optimality cut would have already been here. So hopefully that convinces you that at every iteration I should be getting back a different set of pi's. But I'm gonna now argue that this can't go on forever. There are finitely many pi's that I can get back. Do you believe me, or you don't buy it? And the formula to be thinking of is, how does Cplex give me back pi's? Is this here. Cplex is always looking for an ultimate basis. There's only finitely many. Vertices. This can't go on forever. There might be an enormous amount of them, but this will only happen a finite number of times. So that proves that if I'm not optimal and this thing occurs, it will only happen finitely many times. Eventually I will land here and I'm done. Okay, that's proof of convergence just as far as the optimality cuts are concerned. It's important to remember this, it's helpful geometrically. And on Friday I'll talk to you about the finite convergence of feasibility cuts, and Matthew can take over with the rest.